Hey, sorry, I had to do something else, and I'm breaking, and I'm back here. I'm in a park. You might hear some background noise, but so just going back there. Is the one? Yeah. So okay. So a non-conductive sphere contains positive charge distributed uniformly through all its volume. So this is the case of a insulating sphere with charge, positive charge inside as well as in its surface. That's the difference from the conducting sphere. Conducting sphere, all the charge goes to the extreme part, right, on the surface. And here is not the case because it's a non-conductive sphere and it's all taken by charge. Now, if the charges are positive, and that's the case, which statement about potential? So potential goes always from, um, the electric field goes only from high potential to low potential. That's the direction of electric field. Now, we saw previously, I think we did in class, the electric field for a non-conductive sphere using Gauss law. I think it would be nice to review this here. But, and as we saw, the electric field is pointing outward, right? So outside the sphere goes that way. Inside the sphere is also pointing outward for a positive distribution of charge, which means that the potential should go from the since the electric field is pointing that way, so the potential should be the highest possible in the center part of the sphere and then diminish as you move outside. So that would be the normal conclusion. But let's try to calculate that using and taking the chance to review Gauss law. So when we use Gauss law, what we do, we build a Gaussian sphere or Gaussian surface around it. So the inside charge is Q, right? So we have an inside charge Q, and then and the density distribution of charge is given by Q over volume, right? The volume of that sphere. So which means, and since the distribution is uniform, this is equivalent to the Q over dV. Now, what is the incrementing volume? The incrementing volume is 4 pi r square dr. So therefore the Q, if we need it, is going to be 4 pi r square rho dr. And I took this part from here. Okay, so the electric field points outward, and Gauss' law tells us the electric flux is equal to the charge that happened to be enclosed to that surface divided by epsilon naught. So the right hand side of this equality is such that the enclosed charge for radius more than the radius of that sphere is equal to the total charge divided by epsilon naught. So we have the right hand side, and the left hand side is the Gauss, the electric flux, which is E times A. Okay, so our conclusion is the electric field for radius bigger than r is equal kq over 4 pi r square. R is the distance to the point, right? To here, um, um, divided by epsilon naught. So we have an epsilon naught in there. So basically, electric field falls with the square of the distance. Now, because of that, how can we calculate the voltage? Well, dV dr, dV dr is equal to the negative of the electric field, which is Q over 4 pi, oops, Q divided by 4 pi epsilon r R2. Okay, so therefore dV is equal to the negative of a constant 4 pi epsilon r dr over r squared. And these, let's take this for r all the way to infinity, r all the way to infinity. And then we have for r bigger than capital R, the radius of the sphere, voltage of infinity minus V at a certain point R is equal to, this would be negative, no, it's going to be positive Q over 4 pi epsilon R 1 over R from R to infinity. And then we conclude the voltage outside the sphere is Q over 4 pi epsilon naught, 4 pi epsilon naught 1 over R. Okay, so the voltage falls with 1 over R. Okay, so now what is the voltage inside the sphere? So we do the same thing. We come up with a Gaussian surface now that is here, right, at a radius R. And since we know the voltage at a radius R, which is, we just replace, right? This R is not here. Right? 1 over R. So we have that. So we can then use again the Gauss law to figure out the voltage at any part of the sphere. And and if we does that for R less than R, so the Gauss law is equal to the enclosed charge, and we have to figure that divided by epsilon naught. And then when this is done, E that multiply 4 pi r squared is equal to the enclosed charge. Enclosed charge from here is pretty much um, uh, 4 pi r squared for r third to the third row. Okay, and then 4 pi goes away, the third goes away, and so the electric field inside the sphere is given by, and we did that in class, rho. So we have an epsilon naught over 3 epsilon naught r. So when we do the same exercise, dV dr is equal to the negative of electric field, and we integrate this from R any point to the surface because we have this boundary condition, right? So that is going to give us factor dV integral E dr is going to be VR minus V at the point, point R is equal to, and then you integrate the electric field, it's going to be rho 3 epsilon naught. We have a negative there, right? So we have a negative R2 over 2. And then we can figure R to R, R to R. So this is R to R. And then we do we resolve for that, and then we can find the dependence of V, and we find that V, when we make R equal 0, we find the value of V at the center of the sphere should be the highest value. So see if you can reproduce this. If you can't, just let me know. Then we can do on Tuesday or sometime. Didn't we do this in class? I think we did this one in class. I think we did this one too. Oh, we didn't do that one. We didn't do this one. So what's going on here? A figure shows an arrangement of two negatively charged, separated by this much from a proton positive charge. If the two negative charges are held fixed at their location, the proton is given an initial velocity v. So right there, change the color here. What is the minimum initial? Well, that's the same idea, right? The work done from A to B is equal to Q. First of all, work from A to B is equal to the change in kinetic energy that the system goes through, right? And so the minimal energies or the minimum speed is the one such that the final speed is 0, right? If you give more or a speed bigger than that one, the final speed, once it's away from the grid of the field, it's going to be more than 0. So 0 is the minimum possible, and that is minus the initial velocity. So, and we want to find V basically. So the work is equal to this thing here. But what is the work done by the field? The work done by the field is Q V A B. And then we have to just determine what is V at the point A and V at the point B, right? So and then becomes some simple problem, because we can always assume that at an infinity or at this point very far away, the voltage is 0, and then we can calculate the voltage these two particles exert at point A, which is pretty much K, the first charge, which is a negative 4.5 times 10 to minus 9 coulombs over the distance, right? And then multiply it by 2, because we have two particles, particle 1 versus particle 2, so we multiply that by 2. So we have this part that goes in here, and then we can figure that. Okay. Yeah, I was just checking to see if everything's okay. So we're gonna have a proton has a positive charge, so this product is gonna be negative, and the negative cancels out. Well, this problem is basically the same. So you have an alpha particle, a nucleus, nucleus of helium has twice the charge and 4 times the mass. And when they were very far away from each other but headed towards directly each other, proton has had an initial speed of that much. So we have these two alpha particles kind of far away, and you have the mass. The mass here is given, so we have a mass of both of them, and they were very far away from each other, which means the potential is telling you, okay, consider the potential equal to 0, but they are headed towards one another. And this guy has the initial velocity given, and then what is the closest approach when they are kind of like that? So what is r, right? And then you do the same. I mean, the work done by the field in this case, from infinitive to, that's the infinitive, that's configuration A, infinitive configuration A, which is Q times the voltage from infinitive to A, right? And the charge you have, and the V at very far away is 0, at part A is equal to K, or the charge of one of them, times the divided by the distance, which is the one you want to find, and that is equal to the change in kinetic energy. So the final kinetic energy is 0, the initial is the sum of kinetic energy of both of them. So twice half mv squared, and then you can solve for that. Okay, so basically the work done for here to there, which means from this configuration when they are apart to this configuration when they are very close, is equal to changing kinetic energy half m final speed square, and that should be twice, right? Because they both stops, minus half m and the kinetic energy they have initially, 0.003 c square, and then do the same for the other one, right? So and then you can figure what is QV, because it's going to be given by so this is pretty much Q. Infinitive is 0, right? Minus the initial one is the charge of the other alpha particle divided by separation. And this is the charge of an alpha particle. So what is this? We have a charge Q uniformly distributed on a ring. The radius is given. They have a point charge Q at the center of the ring somewhere here. And you have points A and B located on the axis. What is the minimum work? Same idea, minimum work. So the minimum work is the one that can overcome the field itself, because this you have to calculate the voltage here, the voltage here. So the work from A to B is equal Q VA minus VB. Basically, that's it, right? So find the voltage at point A, point B, and then you calculate the minimum. I mean, it's minimum because you go in a straight line, and the only work this external force is doing is overcoming the field. You could do more if you go in a crazy route, right? But you don't want to do that. You want the minimum possible. And pretty much that's it.